So welcome back. It is my pleasure to introduce Amedee to George. He is a professor at the Structural Biology Initiative at ASRC, right across the lawn here, as well as professor in chemistry and biochemistry at City College of New York. He has made use of cryo-EM to sort out images to look at different subpopulations and in order to attain high resolution structures. And that's something that is going to be very useful as we go into the description of how do you deal with data, how do you process data, and dovetailing on to what Fred was talking about, these new maximum likelihood algorithms. Amedee's favorite ice cream is chocolate, and we'll see if before the end of the week, we can do some liquid nitrogen ice cream, maybe one of these days. Okay, so Amedee, the floor is yours.
Hello, everyone. So I guess with Fred Sigworth, you got everything about the math. So I'll do my best to do everything without the math. So kind of basically looking at the practical aspects of the cryo-EM workflow and kind of there's many programs out there, like which one should I use for this task or that task? Why would everybody be using this one and not that one? Because that's kind of what we are trying to do every day. And so I'll give you my personal opinion on those things, and hopefully it will be convincing. And we'll all get beautiful, optimal reconstructions. All right. So here's our workflow. That's better like that. Okay, where sample prep, as Tom Walls tends to frequently say, is the number one thing we need to take care about, and basically nothing starts before that, and garbage in, garbage out. So data collection is perfect because it's been done here, so I will not comment on that. And so the processing workflow starts with frame alignment, identifying your particles, estimating the contrast transfer function or estimating the defocus of your particles, extracting your particles from the micrographs, sorting them out, figuring out which ones are true bona fide particles and which ones are not, including some 2D classification to see if they look good and promising and you can move forward, or if they don't, and therefore you need to go back to your sample prep. Generating models, so that's actually 3D models out of the 2D projections, which Fred probably talked extensively about. Classifying those data in 3 dimensions because that's the most helpful thing to do, and usually particles are not, you don't have just a single population, you almost invariably have more than one, unless you work on very boring proteins, but I'm sure you don't. So refinement, there's many different refinements, and so in cryo-EM, people tend to talk about refinement of the angular orientation, like basically or let's say the angular assignment of your particles, like what are they on the Euler sphere and what are their translations. So that's what we are refining here, which is not to confuse with model refinement. Then there's a particle polishing, which is to basically redo the frame alignment, which was the first step, but in a more local manner, like basically particle by particle, and also potentially refining also the correction for radiation damage and blurring. And then you have your final map, which you may further 3D classify, further refine in a more local manner. You might use variance map, although people rarely do that these days and it's expensive to compute. Or you might actually use just your local resolution map to look at the variance in an indirect way. to kind of figure out what you need to further refine locally. And then we get to basically model building, refinement of the model, and then either getting back to biochemistry or interpreting our structures. I think I love that quote that I heard from John Curian, which is, we are not in the business of solving structures, we're in the business of interpreting them. And so that's actually where most of your work might start, is once you've gone through that whole workflow and you actually need to understand your structure. All right, so that's what we are going to talk about. I have a few slides, but that are more here as a primer for discussion more than anything else, where I kind of list the different programs that exist for doing given tasks. But more importantly will be to be like, okay, what matters at each step? Any questions before I dive in? All right. Okay, so that we'll skip. That as well. That as well. That as well. Sorry, I forgot to delete those slides. All right, here we are. Okay, so movie frame processing. So one of the major aspects of the resolution revolution was having CMOS detectors, which detect electrons better, but also having the fact that they had high frame rates allowed us to collect movies instead of single pictures. And actually that's probably just as important as properly detecting the electrons and having a high DQE. And so how you basically correct for what you can do with those movies is correct for the blurring of your images that are due either to stage drift or to deformations of the ice, which makes all your particles move around and therefore blurs them. And so the initial way it was done early on was just full frame processing, and that was a Ucsf motion core, which was let's say not the first one to do this, but the first one that people kind of broadly used. And where you basically take each frame of your movie and you just basically, by some sort of cross correlation, figure out how much each frame is moving with respect to the other, so that you unblur your image. Now, one thing that it doesn't take care of is the fact that when you have your holes, let's say with your particles in your eyes, things just don't move left and right, which this would take care of. The problem is that things move in all sorts of directions, up or down. Actually, good question. Is it up or is it down? I'm not sure. And that would be interesting to think about. But beyond that, the fact that these things move up and down means that if you look at your micrograph from the top, you have your particles, let's say this one will move slightly to this side, on this side, this one will go this way, this way, this way, and this one might not move very much. And so it's important to correct for that. And so Ucsf motion core was updated to actually incorporate a system where you would basically break down your micrograph into small squares, and then you, after having done the overall frame alignment where they are all mostly in register, then you further optimize locally the position of each of those squares, and you do some interpolation at the edges, basically, of them. And so that's a particularly important step, which is done by Ucsf motion core or I think it's motion core 2 now maybe, properly, and that's actually what you get done automatically at SCMC when you collect data here. And so you get your basically motion corrected micrographs straight away, which is pretty nice. You can also use CryoSpark for doing that. CryoSpark does this. It's actually use let's say an accelerated algorithm that was initially aligned parts by John Rubinstein, but basically does very similar thing. And then you have a third one, which is getting quite popular, which is called WARP, which also does this and also tries to kind of correct for a number of geometric aberrations in some way that you may get beyond just movement of those squares with respect to each other. So these are, let's say, the three major ways people use either the motion core, CryoSpark, or WARP. These are the let's say the classic ones. Now you have other ones like XMIP optical flow, which has been tried by a few people and might work as well. And there's a bunch of other ones around. All right, there's one place where this becomes actually quite important to actually correct properly is also when you tilt your data. So if you're basically your micrograph now is like this, and your particles are here, now the doming that we had and that was making small movements, like in the initial case you were seeing a fairly small movement for something that might be much larger in the Z direction. So you see you have like big movement in Z and small movement in XY. But now when you tilt, the movement in Z becomes a movement in XY, and so therefore you have large movements of your particles. And so in this particular case, being able to properly correct for the sample movement becomes a lot more critical. And also it's let's say one of the things that makes tilted data collection tricky, which is that suddenly everybody moves a lot more. And so that's actually why that's nothing to do with processing, that when you tilt, you definitely want to have ultra unifoil gold grids. You can't really use carbon grids because basically the movement is so great that your images are completely blurred. Whereas with gold grids, you have less movement and you might get away with pretty high resolution despite the tilting. Okay, so yeah, here if we think about it, only Z is here and what was XY now? All right, let's not mess up with that. All right. Next is estimating the defocus of your images. So when you collect data, you set particular defocus or defocus range in your microscope. But the defocus that is set by the microscope and the defocus you actually get in your images are not necessarily the same. One of the reasons, for example, is that the defocus is actually measured away from your image. And so you could potentially get to a point where you basically set your defocus and know it very well by doing maybe multiple defocus points around your image, something like that. But in some ways that would be extremely time consuming and not really useful because you can estimate your defocus pretty accurately straight from the micrographs. So it used to be before the direct detector that you were always trying to get some carbon in your image so that you have enough signal to measure the defocus. Nowadays, because the direct detectors have so much higher signal to noise ratio, just plain eyes is enough to actually see basically your CTF rings clearly enough to get a good estimation. So again, lots of ways to calculate defocus. CTF find 4 is a quite popular one. GCTF used to be a very popular one as well. Now, the most used ones are the ones that are incorporated either in CryoSpark because everybody used CryoSpark, or in Reliant because everybody used Reliant as well. So I think in Reliant we still work with CTF find 4, whereas in CryoSpark you have what's called patch CTF, which actually is like as soon as you tilt your data, it's critical. If you don't tilt your data, it's not as critical, but it's actually quite important. So the idea being that your micrograph, again, might not be completely flat, and so the defocus in this corner might be slightly different from this corner, and this corner, and this corner. And if you think about the doming that you might have, you might also have, let's say, I don't know, a different defocus in the centers and on the sides. And so, again, cutting your micrograph in patches and estimating the CTF on each of those patches will get you a much more accurate defocus value for your particles than if you just look at it overall. And so CryoSpark patch CTF does that pretty well. Let's say well enough and robustly enough that even if you think about tilted data sets where that becomes really critical, patch CTF will tend to get you good values for your defocus for particles that are on this side and on this side. Whereas GCTF will get it sometimes and will fail some other times, and so not so ideal. And CTF find 4 had was probably the first program that actually implemented basically an estimation of the tilt. But again, I think it's, if I remember correctly, it's quite a rigid version of it where you just try to find the tilt angle. So you're not really trying to see if there are more variations within your micrograph, which usually there is. Okay, and actually patch CTF came, if I remember correctly, after WARP did its own patch CTF, which is extremely accurate. And actually, I mean, in my hands, that's where we started getting good resolutions, tilted data, because suddenly we had good estimation of the CTF of the different particles, which is quite critical. So then Reliant is not here, obviously, because it doesn't have its own CTF estimation pipeline, except if you get to what's called the per particle polishing, and also per particle defocus estimation. And so I don't think it's on the next slide, add Reliant per particle. But the problem with, let's say, not taking care of it before that per particle step is that having a correct value for your CTF is actually critical for estimating the orientation of your particles, because basically the cross-correlation values between the reference and the particles will be completely, well, let's say wildly different if your CTF is correctly estimated or not. Up to the point where you can actually have, if your CTF is too wrong, you can have a negative cross-correlation peak instead of a positive one at the correct orientation. And so having the CTF very well figured out early on will allow you to actually keep all those good particles that didn't have very much signal maybe, or that were kind of quite far off from the initial CTF defocus value, which would actually be thrown away or misaligned in 2D or in 3D refinement and classifications. So especially for tilted data, for example, it would mean that if you just started with a single CTF, a single defocus value for your whole micrograph, or a poorly defined value based on kind of a rough idea of the tilt, it would mean that many of your particles, maybe 50% or even 90% of them might be misaligned. And then you cannot really retrieve the information back in the reliant per particle estimation, because it relies on the proper alignment of your particles as a starting point. So if they are misaligned, Reliant cannot re-estimate properly the CTF value more accurately. So they are wasted anyway. Yeah.
You suggest that you could start, you could just skip the whole micrograph CTF estimation and just do the per particle CTF estimation at the beginning.
So question you're asking is, could we skip completely CSF estimation at the start and just going straight to per particle CTF estimation?
Is it even possible?
You basically don't have enough signal within each particle by itself to get an accurate rough estimation of the CTF. So you'll get wildly off values, which will not allow you to actually align your particle to a reference in the first place. And so you won't be able to actually get anywhere. So basically the per particle CTF estimation in Reliant, in CryoSpark, everywhere is done in a very local fashion where you've already aligned your particle extremely well to your reference. You have already a reconstruction as 3-4 angstrom resolution. And now you're just doing a very local alignment of your particle, and together with basically trying to refine within a small range what the CTF value might be. And then in that case, you manage to get to basically a good local, well, a global optimum. Yeah.
So we needed to do the level CTF correction correctly. So the result will be even worse if we use the mechanical CTF method.
That's correct. So you're saying basically, if the initial CTF estimation wasn't done properly, the per particle CTF will actually make things worse. And the answer is potentially very much yes.
It's like only when we reach like 3 angstrom resolution.
In terms of resolution, that's a good question. I had the previous assumption that you needed at least 4 angstrom resolution to get to be able to properly estimate per particle CTF, because basically you have your, I'm going to do a very rough kind of 1D CTF. Oops, it's not exactly what I wanted to do. All right. You need that kind of good data in this portion at high resolution. So that's your 6 to 4 angstrom, let's say, where you have let's say oscillations that are close, that are quite rapid, and so therefore a small change in value will change the phase of those oscillations very drastically, and so you need that data to be able to get a better fit. And so if your reconstruction is at, let's say, 6 angstrom, you actually get better data from the whole micrograph, because the whole micrograph can estimate CTF all the way up to 3-4 angstrom resolution. You still see the oscillations in the micrograph. And so you basically, you want your reconstruction to be in that same range. That's my understanding. Now, it's possible that even with 6 angstroms, you'd get things that, like oscillations that constrain enough the estimation that you'd still be able to improve things. But yes, the limitation should be the reconstruction resolution, not the CTF estimation that was done initially. Yeah.
Actually, is there a recommended defocus range to use? Because as I understand it, if you use too far of a range, then you're going to get like kind of too distorted of images at some point. But if you use too small of a range, then you have zeros that are too close to each other. So is there like some recommended range so that you get a good like?
Okay, so the question is there a recommended range for data collection specifically? And that's a very good question, to which I don't have a good answer, because I have not seen, but there has been studies about that, but I haven't seen like the gold standard study that tells you this is it. And so if someone wants to do that, that would be fantastic, because it's actually an important piece of the puzzle. So the thing to think about is that if you, and I'm going to erase that. So if you have a low defocus, you'll have, let's say, one or two, you'll have very few oscillations, but very little contrast. So that's why we don't like it. And so here the question is, how low can I go until I can no longer align my particles? I think that's probably the experiment to do, which is to go as low as you can, probably with a different range of samples that have different features, and see at what point the alignment breaks down, so that we have a hard limit. Okay, can't go below X. And so far it looks like we can definitely go below 1 micron defocus, probably pretty close to 0.5 micron defocus. But where exactly you start to lose alignment accuracy, which basically throws your resolution out of the window, I don't know. And yeah, I was actually discussing with my postdoc to actually do some experiment along those lines, but we haven't done them. So if someone wants to do them, I'd be interested by the result too. Okay, so, but here it's kind of an ideal situation, the low defocus, because it's kind of, even if you don't fit perfectly, if you don't have a perfect number for your defocus, the difference is going to be very minor here. Like you're not going to be out of phase if your wave is kind of slightly off like that. Okay? And so you'll still be able to align your particles properly, and you won't have too detrimental effects. Whereas at higher defocus, you'll have more contrast at low resolution, but then it's going to oscillate a lot more. And there, that same small difference is actually something like half a phase. So here you're actually quite far off in terms of where you're supposed to be. And so at high defocus, very quickly it becomes impossible to get the correct value at high resolution. And so basically you get disruptive interference, like basically all your particles that don't have the exact correct defocus value will have, basically their high resolution data will be thrown out of the window, because it will be basically out of, it will produce destructive interference at high resolution between the CTF value given to the reference and your actual particles when you align the particles and when you reconstruct. So I said that I botched that last phrase. that last sentence, but I think you get the idea. All right, so again, now which defocus value is still fine to get high resolution data? Again, I haven't seen a kind of a good study on that, and that study is easier because you can basically just reconstruct volumes for different defocus values and see at basically the B factor of those different reconstructions and see at what point you're starting to really lose in the game. You are collecting at different defoci so that you fill the places where you have basically your CTF is at 0. So you're filling the zeros in the CTF. And so as long as you have enough of a range to fill those zeros, you're fine. And the range is probably very, very small. Like you don't need that much of a range. And again, that's another study that we might want to do, which is, yeah, what's the minimum range you can do to have all your zeros filled? And given that now we are looking at things at high resolution, maybe we don't care so much about filling the zeros at low resolution. And so if you have a few holes at low resolution, it doesn't matter. And so at what, yeah, basically, what range would be the minimum needed? Okay, and so now from my experience with very small particles, currently I collect data between, let's say, 0.7 and 1.5 micron. And I've seen others doing even less than that, maybe 0.7 to 1 or 1.2. And that for very small particles that don't actually have that much contrast. And so that seems to be working, and therefore, why should I be collecting anything beyond 1.5 angstrom if I can get good reconstructions at 1.5 and lower? I don't know. So, but now it's still a very empirical kind of with the nose. Yeah.
So I want to go back to the previous statement about when using the particle pollution techniques when you do the frame CDF correction, and you may lose some of the good particle at the step where you want to do the particle pollution. Is there any way to retrieve back and get those?
Basically, as I said, we lose particles if they don't have the correct CTF estimation in the first place because they are misaligned. Can you retrieve them? Well, you would need to find again what is their optimum CTF. So, and how do you figure that out? That's going to be tricky. So basically, to retrieve them, maybe it's actually re-estimate your micrograph CTF. Or maybe you could have a trick where you kind of look at the CTF value of all your particles per micrograph and see whether you can sort of see a trend in the noise. But it's probably going to be difficult because like only a few of the particles will have a correct CTF and many of them will not. And so which ones do you take? Well, I guess you would take the ones that contribute to the reconstruction, but it's also not easy to sort out who contributes and who does not. So I would say quite critical to get a good CTF estimation in the first place with a patch CTF program that is robust. And the two that I know are robust are the CryoSpark patch CTF and the WARP patch CTF. And both of those have shown basically beautiful resolutions even without doing any polishing afterwards. Yeah. Okay. So yeah, last little thing on the per particle. It's like the patch CTF still gives you an average CTF value for that patch, So it's not completely accurate. Therefore, the per particle still remains useful for two reasons. One, yeah, the patch is not that small, so you might have variations within the patch in X, Y, but also your particles might be sitting at different places in the ice. And so you might have something to gain at getting the exact CTF or defocus value for your particle, because one might be at the top of the ice, the other at the bottom. And if your ice is not very thin, that might be quite actually important. And therefore you'll gain a lot in such a case. Like in the case of thick ice, you'd gain a lot by doing per particle CTF. Yeah. And when people do warp or patch CTF and then do per particle polishing in Reliant, for example, or further estimation, like local estimation of CTF per particle, resolution tend to improve, meaning that you do actually get better values. Yeah.
So I'm definitely a novice at data processing, but I've tried going through the process of CTF estimation using Reliance, so the CTF4 and the GCTF. And I'm trying to remember, I don't remember if there were that many parameters that you could kind of like adjust. So if you're having issues with CTF estimation, what would be some of the parameters that you could kind of play with to try to?
Excellent question. So what parameters can we play with in CTF estimation to improve things? And I have not reviewed all the parameters just before the lecture, so I will try not to forget the most important one. There are two that come to mind. One is the range at which you fit your CTF. So let's say most of the time it's somewhere between 20 angstrom and maybe 4 angstrom. And some people push it to maybe 3.5 angstrom or so. So you can play with that. So 20 angstroms, that's something you can play with a little bit potentially, because you have kind of the data at low resolution is not very accurate, or it is, let's say, not very well modeled, I should say. So we don't really know what's going on there. Therefore, the fit is not very good. So that's why we usually cut at 20 angstrom to not basically introduce, to not try to fit things we don't know how to fit. Now, the precision, you get it from the high resolution. And so you might say, well, should I fit at 4 angstroms or at 3.5 or at 2.5 angstrom? And there, the trick is that the further you go, the more noisy it is. And so the more spurious you might get a result. And so if your program tends to fail completely, I would restrict to lower resolutions to make sure I get a proper fit of the low resolutions first. And maybe I'll try to refine that higher resolution once I have that low resolution properly fit. So maybe I'll fit now. And so that's going to be really data dependent. Like, should I fit at 6 angstrom where I don't have that many oscillations, so it's actually potentially difficult to catch on any one of those, or should I go to 4 angstrom? One thing that I've seen regularly is that going beyond 3.5 angstroms is not a good idea, because you're really starting to be overwhelmed by noise, and therefore you're going to basically fit to noise instead of to data, and that's not a good thing. And I've seen, at least in WARP, I've seen CTF estimations failing completely by going too far into the high resolutions. So I think, and from experience from others in the field, it looks like somewhere between 4 and 3.5 angstroms is what people do. Then there's another one which you don't have access in every program, which is kind of you can give a B factor to your micrograph before you do your fit. Basically, you can give more weight to the low resolution versus to the high resolutions, and that would have potentially quite an impact on how basically how you're fitting your data. And so, yeah, basically more low resolution data will give you a more accurate overall fit, but less precise. And more emphasis on the high resolution will give you a less accurate, more precise fit. And actually that B factor is also used when you do the patch alignment of your micrographs. And so that's also where we used to play a lot with when it was the early days of those programs. Now they are probably kind of fairly well set, but that's something you can play with, like playing with a B factor in your frames and with a resolution range at which you're filtering your micrographs when you do that fit to make sure you get it accurate. Yeah. Does that answer your question? Okay. Next step in our workflow is particle picking, which used to be a massive bottleneck. And actually, the funny part is that last time I gave that lecture, or last time I made my slides, this part was not in them. And so it was still a fun mess. Okay, so basically nowadays, most of the time, you can sort of get rid of all of this, because that's when things were messy. And nowadays, we have basically deep learning or neural nets that figure out very well what you want and what you don't want. And so therefore, these are basically the gold standard for particle picking. And in virtually every case, this is the only thing I would use. And in WARP, you have it pre-trained, and you can just get going, and it tends to work. In Topaz, I think, well, I don't know if there is a repository of trained nets. Yeah, a general model. So that would be great, a general model for Topaz. Maybe it would be nice to have kind of a database of different models for different things at different sizes and so on, so that people would be like, oh, I'm working on a GPCR, here it is. I'm working on a virus, here it is, and so on. Now, very often you will get better results with all of these if you retrain with your own data. It will allow the program to pick some, like basically your particles will always have more contrast in one orientation than another. And so by retraining, it will allow the program to actually pick those rare views that maybe don't have that much contrast and that you kind of missed. And very often you'll get more particles by retraining, even though it's a pain in the neck. And most of the time we just don't do it. We just browse through and just do like whatever we have to do and never get back to it. But matter of fact, you could potentially gain 10–20% more particles by retraining. And so, yeah, if you're pushing for resolution or if you have a preferred orientation, that's a good case where retraining might be a good idea, because when you have preferred orientation, you might have some rare views hidden somewhere. I think I had a case of a small GPCR where some views just didn't show up or would not align properly, and so they just didn't have enough signal to be picked and aligned. And so retraining allowed to pick them, and then it was a matter of trying to figure out a good strategy to get them to be properly aligned. Yeah? What about the case when you don't know what your particle look like? Excellent question. In a case you don't know what your particle look like, you know it's a protein or protein RNA or RNA complex. Therefore, the general model that's been trained on many other data sets of different kinds will have some features of your protein. Therefore, will be the best thing to use to start.
And would like these neural network-based programs, would they already get trained on a general model, or?
Most of them have general models already available.
So you could like bootstrap your way up
Yeah,
to figure
exact. So you can get a first pick, get 2D classification. Oh, that's how it looks like. Okay, now maybe I'm gonna retrain. Like, oh, you missed this one and this one and this one. Retrain, get 50% more particles, and off you go. Yeah.
So let's say your data set has some purple orientation. Would it then be a bad idea to create a model from your own data set and train using these tools? Because then even the model would have that purple orientation.
So you're asking like, would it be a bad idea to retrain because it would have that preferred orientation embedded in the model, basically?
Yeah, so basically whatever.
That's possible.
When you train using your own data set, then the model would have the preferred orientation. So it's not going to help with picking other particles.
Potentially, but now the models are not that accurate. So yes, they might pick up on the orientation, but they also pick up on the size of the particle, some other features that are orientation independent. And so it will tend to work anyway. But yes, you have a good case, which is like you might not want to train it to only pick the preferred orientation because that's 95% of your data. So you definitely have a good point, and so we should definitely be careful with that.
So would you recommend just like not doing manual picking at all? I wouldn't be more on
Oh, I didn't cross out manual picking. It's a fantastic exercise you should do. And when you train, that's what you do. So as you can see, I crossed up to here.
Are you saying to do manual picking first and then neural network? Or when you say retrain, are you saying use the neural network-based picking and then?
I think you'll be always better off doing the neural network because it will see what you don't see. And yeah, you can do a quick 2D classification and be like, okay, this is what's supposed to be good. Now it's just missing a few that look similar. Whereas when you pick manually by yourself, I cannot count the number of projects that can have fantastic preferred orientation because the picker was only picking that one view that was super contrasty and was missing everything else. And so yeah, manual picking is dangerous because you are much more biased than a neural network. Yeah.
The problem that I have is that most of these basically a circle or like an out chain, but I have like basically a stick. So I have to manual picking because like none of the block pickers are working for me and use that to train the toolbars. I mean, is there a way to get around the manual picking?
No, yeah, there's actually a paper by Schwarzer that came out not so long ago about picking amyloid fibers, where they used topaz and did some refinements of topaz to better deal with those elongated things. And so maybe that's one to look for. But yes, when you have filaments, those neural networks are not very good at that, and usually you do need to train them first yourself before getting to pick your whole data set.
And how would I do it? So basically, if I manually pick, I miss like a lot of the orientations. So how would I do it to start off with manual picking and then evolve the neural network to get everything like what would be the best?
Well, one could be you let the neural network do its thing, and you see everywhere where it's wrong, and you correct for that. So you let it run. Yeah, you ask it to do a blob, and it will pick maybe some of your particles that are head-on view and are a blob, and maybe we'll pick everything you didn't identify as your bona fide particles, but then all the ones that you know are your particles, you just need to add to that. But maybe it will not pick any of the things you want, which is frequently the case. Like I have some stuff where it just doesn't pick anything that I want, and then you just need to train it manually by manually picking everything and hoping that he will catch the things you didn't catch. Yeah, there's also filament tracer particle picking, which is a different type of particle picking. Okay, we are kind of running. How much time do we still have? Because we are running a little.
15 minutes. We'll have a working lunch because we'll have a round table.
Yeah.
Which is actually already out there. So
I think I'll skip to what's the most important stuff. So particle sorting. There's many ways to sort particles, and let me see. And let's say 2D classification overall is good as a. Someone was taking a picture and go slow enough that the picture can be taken. 2D classification is used a lot as a check and to remove some definite wrong stuff. Generally works very fast in CrowdSpark, works well in Reline if you know how to tweak the resolution range at which you align your particles. Yeah, there's not too much to do or say about it. There's actually, maybe there's one comment I would make, which is be actually very wary of removing particles in 2D, because if you have all your orientations then it's fine. But very frequently where you have a preferred orientation, which is the culprit of so many datasets, 2D classification will only catch potentially all your good views that you have millions of, and will potentially miss the rarest views just because there are not enough of those particles, and they will be somewhere diffused into some random classes that you would not pick. And so, or they might show low resolution, so you might be, oh, that's a low resolution view, where the reason is that maybe there's very few particles in it. So there's basically the 2D classification is kind of very dangerous to remove things from 2D classification. And so I tend to use it to maybe remove like gold edges or things that definitely have nothing to do with the particle, and I'm 100% sure about it, but I tend to keep everything that I'm not sure about. And basically remove them in 3D classification, because as soon as I can generate a 3D model of my particle, the 3D classification can be much more powerful at removing bad stuff that don't look like the reference, while keeping the rare views. Okay, so I won't get too much into those details. You might never have heard of Spider or eMagic, and that's fine. And let me see. Yeah.
Say if you have 100,000 particles, what would be the recommended classes that the classifier would?
If you have
100,000, how many classes would you recommend to classify?
Good question. How many classes should we use in 2D classification? That's kind of one of the major parameters in your classification, so that's the right question to ask. In my experience, you get good-looking classes with 500 particles per class. You can still get pretty good classes with 200 particles per class if you have good signal in your data. Less than that, starts to become more tricky. I've had beautiful classes that have only 10 particles, but that's for, I don't know, a beautiful ribosome that has all the signal you need, or like, they don't happen very frequently. Anyway, so I would say 200 to 500 particles per class tends to be my target. Now, you don't want too many classes, because I read some things about that. Let's say the optimization is tends to fall apart when you start to have too many classes. So, and Fred would probably know more about that than I do. So somewhere between 50 and 100 or 200 classes is going to be what you want to shoot for, depending on the size of your data set. One thing that's very helpful, let's say you don't really care about 2D if things work, you just use it as a check, but it's maybe when things don't work that you play with 2D a lot more. And one thing that I found helpful when you have a class, you're not sure what it is, whether you should include it or not, is to take that class just by itself and subclassify it, maybe in an extra 10 classes. And that's where you'll see whether the extra 10 classes are just as random as your initial class, or if actually you had a shape that was still always the same, or like you still have that defined shape from that initial class. So that can be something that's kind of helpful. And there is examples. I think Oliver Clark had an example of a membrane protein which was kind of blurry and didn't get to very high resolutions until he did 2D classification per view. So that all the particles had been aligned. You divide them by bin in terms of, like, I don't know, every 15 degrees, something like that, or every 10 degrees on your sphere based on the alignment parameters. And then you classify each of those views separately. And by only keeping the class that was like the shiniest, like where you could see definite 2D structural elements, and only taking those, then suddenly you went to 3.5 angstrom resolution. Because basically the blurriness was not easy to sort out in 3D in his case, or maybe he didn't find the right parameters in 3D classification to get rid of basically all those particles that are true, they were true membrane protein, just more fuzzy. Okay, so before you get to 3D classification, you actually need a reference. And that used to be a major problem in single particle EM until direct detectors came about. And would anybody tell me why direct detectors helped with that? Because basically all the things I'm showing here existed before direct detectors. And before direct detectors, we always run into problems. And there's been a bunch of Einstein in the noise structures in the literature that were just basically whatever the reference was. Yeah. Okay, so I'll answer the question for you, which is that the method we use to get an initial 3D reference out of nothing is something that was initially made important by Aaron Klug in the 1960s, which is a common line. The fact that in Fourier space, all your particles share a common line with every other particle in your dataset. And therefore which is basically to say, here's one particle, which in Fourier space would look like a blob like that. And then if you have another particle, which look basically roughly the same, but a different orientation, it would basically fit within the initial particle, kind of like that. So they would share a common line. And so you could find that common line between those two particles. Obviously here you only have 1 degree of freedom, which is a rotation around the central axis here. And so you can find which angle basically that common line is, and now you figured out one of the orientations between those two particles. And now if you have a third particle that maybe slots in, let's say this way, now 3 particles constrain each of them completely. So it means that basically if you find a common line between all those 3 particles with each other, here you are. You have an initial 3D reference because you can take those 3 particles that have been aligned to each other in Fourier space, and now you just do an inverse Fourier transform, and you get your 3D volume, and done. And so obviously that would be a crappy 3D volume because you only have 3 orientations. But if you do that for 100,000 particles, obviously that 3D volume is going to be pretty sharp. Okay, and so now, where did the problem come from initially? Yeah?
Is there any quality relationship between like how many particle orientations such as like resolution of your 3D validation model here and quantitative?
So quantitative relationship between number of particles and final resolution, basically. That's kind of the idea, like how many orientations do you need to get high resolution? I'll get to it. So I'll get to it next slide. Okay, so the reason why the resolution revolution or the direct detectors solved that problem of getting initial references is that suddenly, compared to before, the signal-to-noise ratio of our images is much, much greater. And as a result, that common line, which was findable in a ribosome before, and most of the time not findable in anything much smaller than that, basically because of the low signal of the film micrographs or the CCD camera, basically meant that very often you had wrong initial references because the common line algorithms, the common line program, that's my word, just couldn't figure out the correct answer. And still today, we can have mistakes. But nowadays, our reconstructions most of the time go sub-nanometer or sub-6 angstrom. And so sub-nanometer, you see alpha helices. And so you can, if you see alpha helices that look really much like an alpha helix, it means your model was right, and therefore you can keep going. And if on top of that you see the pitch of your alpha helices, like it's a pretty foolproof result, which means that your initial reference was correct, and you can just keep going without thinking about it ever again. And so whereas before, and still nowadays, you can still have problems when your resolution is not good enough to see alpha helices reliably, which is somewhere around 8 angstrom resolution. You might be stuck at, I don't know, 10 angstrom, 9 angstrom resolution. You're like, looks like I have something. It looks like a protein. You cannot really, I think I see alpha helices or I see elongated densities that might be that, but not so sure. And in those cases, your initial reference might very well be wrong. Because basically, if your common line algorithm didn't work, it's probably because, well, if you didn't get sub-nanometer, it's one of the reasons is actually your common line algorithm didn't work, and therefore you cannot go much beyond that, or at least it would be artificial. And so you look at something that tells you, oh, I'm at 5 angstrom resolution, but you don't see any recognizable feature, most likely, yeah, your initial reference was wrong. But that doesn't happen very often. It happens for flimsy particles that are really flexible, or you don't know, but you actually have a very preferred orientation, you only see one view. Or for symmetry, like when you have symmetry in your particle, it can easily get difficult to sort out what's the correct solution in common lines. And so there are still times when it's a bit messed up. And so there are still two methods that work and that are pretty much foolproof. One is random conical tilt, and one is actually, you can actually use tomography nowadays. And a nice paper that we wrote with SCMC on actually how to get initial model regeneration out of tomograms. So random conical tilt is you take one image not tilted, you take the second image tilted of the same field of view, and you know by how much you tilted, therefore you know the difference in orientation between the first image and all the other ones. And all the other ones, you know, they are within a cone around around an axis, and therefore they all are related to each other based on the rotation of the initial picture versus the new picture and the tilt axis. So let's say you're geometrically constrained, therefore you can get a reliable initial reconstruction, and people rarely use that, but I'm actually wondering whether with gold grids and direct detectors, whether you can actually go to pre-high resolutions straight out of a random conical tilt. I mean, you'll be limited by the number of particles that you use in those cases, but you might be able to go sub-nanometer. The other one is tomography, where you actually take a few fields of view of your particle and you tilt at every possible angle, except this one actually, because you can't. All right, this is bad drawing because it's hard to draw on that thing, but you get the idea. Basically, you tilt your stage and then you align those tilted images and obtain basically a whole 3D volume, not of your particle, but of your field of view, basically. And so then you can, within that 3D volume, some of it will be your ice layer, and within that will be your particles, and you'll have actually a 3D view of each of your particles. And given that they are all oriented randomly, you can do subtomogram averaging and get a nice 3D view of your particles from tomography. Now I don't know, actually I don't have a good sense of what's the minimum size of your particles to get a reliable subtomogram average of those particles. Like in single particle, we know we can get all the way down to approximately 40 kilodalton. But in single particle, you have one image with a lot of those and kind of very stable and so on. When you do tomograms, you're tilting your stage, you have lots of movements as you tilt, you're trying to realign all the tilts to each other. There is doming at the same time. There's a lot of issues. And so your 3D reconstruction, your tomogram, is not necessarily as high resolution as you'd want it to be. And so the subtomograms also will not be at as high resolution as you'd want them to be. So how small the particle can you reconstruct by tomography? Actually, I would ask SCMC if they have experience in that. We've reconstructed something that was around 5,500 kilodalton, which was a helicase, and got an initial model out of that. Yeah?
So if you're doing a random
incremental tilt for tomography just for reference generation? Do you have to do it for the entire data set, or could you just do it for a subset?
So do you have to do random conical tilt or tomography for the whole data set? Answer is no. It's only to get an initial reference. And that reference can be very low resolution, that's fine, because usually you don't use higher than 30 angstrom resolution when you start aligning your particles anyway. So you need a reliable 30 angstrom resolution reconstruction. That's all you need. And so a few micrographs or a few fields of view, even potentially a single one, might be enough. Yes?
Did you do it in cryo or just in native state?
In
This was all done back in the day, right?
So the tomogram of the helicase was in cryo.
The random conical tilt?
And the random conical tilt, I have not done it with gold grids. I presume that we would make it work with gold grids in cryo.
Don't you lack a good orientation with random conical tilts if you had to echo?
Good question. I think yeah, good question. Tomogram might be the better way forward in any case. I know for orthogonal tilts, you definitely don't want preferred orientation. Yeah. Okay. And then if you're still not sure and you want to know if your low resolution reconstruction is correct or not, there is something called a tilt pair test. You can find the paper for that. This is actually quite important. I mean, it was very important before we could get reliable sub-nanometer. Now it's less important, except when you actually don't get there. And so the tilt pair test is basically you take, for a few micrographs, you take two images, one tilted and one not, and you know by how much you tilted. And then you say, okay, you align those two particles, the tilted and the not tilted, and you know you tilted 10 degrees or 20 degrees, and therefore the difference between those two particles should be exactly that number, plus minus the uncertainty of the alignment. And so if it's not that number, if the number is random, you know you don't have the correct reference. Yeah, so I encourage anybody to look at that, because it also tells you the accuracy of your alignment. Am I accurate at plus minus 1 degree, or am I accurate plus minus 10 degree? And that will tell a lot about the resolution you can achieve. Yeah.
For tilt pair test, would that be at the same location on your grid? 0 and whatever tilt degrees that you're using?
Yes, it's at the same location on your grid because you want to see the same particle twice.
So with that, after that amount of electron pulses, does it become more difficult to align your particles because of degradation of the electron?
So yes, you have radiation damage, and therefore one of your two particles will definitely not get to high resolution. But if you didn't really burn the first dose, at the first dose, you still have plenty of data in the 10 to 20 angstrom resolution range that you need for aligning your particles. So both particles will be aligned just as accurately, basically, plus minus epsilon. Yeah?
You just treat it like a two-tilt tomography, you just split it just in half on two pairs, two tilts, tilt pair test.
Yeah, you could do whichever, but why doing two tilts and not just one flat and one tilted? I mean, yeah, maybe maybe it might make it easier at matching the two, but beyond that, I mean, it's the same principle basically. It would work the same. Okay. All right, so I think that will be kind of the last thing we'll be talking about. Then you get to 3D classification and 3D alignments. once you have your reference. There's a bunch of ways to do 3D classification or 3D refinement. XMIP ML3D is basically the old Reliant in some ways. Reliant is what everybody uses. CryoSpark is extremely fast. That's why everybody uses it as well. You have a bunch of other programs. FreeAlign is also used in some cases and has some features that you don't have in the other programs. So basically, each of them has its specific features that you will want to have. And so, for example, CryoSpark is very fast. So you'll want to do that for anything you want to do fast. So when you have your initial data and you try to sort out what's crap and what's not, you'd rather do it with a fast program because you have a lot of particles. And so CryoSpark will be good at that. And also with CryoSpark, there's one type of experiment you can do, which is you can do a 3D classification where one reference is your good initial reference that you like, and you can give it 3 or 4 other references that have nothing to do with it. A ribosome, a strip V1, like things that have different shapes, and then you say, okay, my 500,000 particles, who goes to reference 1 and who does not? And that way you can sort out very quickly in 3D without losing your rare views. You can sort out the junk from the good stuff. Just do 2 or 3 rounds of that, and you end up with a very clean data set. Yeah?
To that point, if you have a single reference, a single good reference, but your data set actually contains like a small subset that's in a different conformation that might violate that reference, how do you not lose those particles and hang on to that very biologically interesting conformational change?
Very good question. Like, what if there's conformational variability in that one reference, and you might lose some particles if they don't align to the average of all these conformations? And so you can definitely, because CryoSpark is fast, you can actually, if you know there is variability somewhere that's important, you can break down into 3 good references and 5 bad, and it's going to work just fine. You can do that. You cannot do that in Reliant. One, it's very slow. It's slower, so it would be expensive to do, but not impossible. But there is some quirks in the Reliant statistics, basically the statistical framework, which make it break down when you have references that are not basically all the same. So if you take references of the same thing at different resolutions, filtered at different resolutions, or different things, everything collapses to one reference, and the other 4 or 5 that you have will be black, like no particle will go to it. The reason for that is totally obscure to me. It just happens to be like that. And I try to play with it a lot, never managed to find a fix. So there's some statistics don't get properly initialized, basically, and as a result, it goes to hell. But CryoSpark, for whatever reason, even though it uses kind of not the same mass, but there's a lot of things that are ported from Reliant, it doesn't break down that way, so it works. I don't know if you can do it in FreeAlign. So that's a good way to get rid of everything you don't want while keeping your rare views, and that's the important part. That's why I'd rather not use 2D whatsoever, go straight to 3D and do that, and then use 2D whenever I need to kind of understand my data set better. Okay, there's another thing. So that's for cleaning things up. And then we get back to that question, like how many particles views do you need, and to get to high resolution. But also, that's actually an important point to think about when you classify data. It's like, basically, let's say you have your Fourier volume, which is some kind of blob, and you're trying to fit 2D slices to it in all sorts of orientations from your data set. And whether they go to this reference or to that reference in a classification, for example, is basically, okay, like my particle 1 here, does it fit better this in 2D, this 2D slice, or does it fit better that 2D slice here? And you're doing some maximum likelihood statistics to figure that out. There's one particular point which is not well addressed in Relion, which apparently is properly addressed in CrossSpark, which is that how fine your sampling in terms of angles here is critical for the accuracy of that fit. Therefore, if you're doing your classification in Relion with global search, basically where you're basically searching the orientation of your particles every 15 or 7.5 degrees globally, like through, like over the whole sphere, it means that the angle between, like, your particles will try to align to each reference every, I don't know, 15 degrees, for example. And it might fit relatively well to one angle and less well to the second one, and so on. But then if you look at reference number 2, same 15 degrees, with that accuracy, it might say, oh, I prefer number 2, actually. Number 2 seemed to be better. Okay. When in fact, it's just that the difference in conformation of 1 and 2 was basically too small to figure out at that angular range. It's like basically 2 was kind of happy, 1 was kind of happy, but none of them actually had the right orientation parameter, because they both would have wanted to be maybe here. And so therefore the choice was made bad. And so therefore what you really need to be careful about is to go to an angular range where you can actually make the discrimination between two conformations. And from my experience, having played with that a lot, the choice is made properly somewhere around 2 degrees. So you need to go all the way down to 1.8 degree in Relion to make that choice, which means that you no longer look broadly at the angular sphere, you're looking at it locally within plus minus 10 degrees. And there's another problem with that, which is you might constrain your classification by that angular range. So you need enough range that the particle can jump from one class to the other, and enough sampling that you can make the proper choice between the two solutions. And I found at 1.8 degree, I can have enough range to not constrain while having pretty much the right choice. But usually particles are definitely happy 100% once you get to 1 degree. But in that case, you do get some constraints. Yeah?
So do you know funnel at 50 degree and then 7.5 and 3.7 and then 1.8 through multiple rounds of 3D?
So do I funnel from 15 all the way down to 1? The answer is, when CrossSpark didn't exist, the answer was yes. I would take very low resolution, like 100 angstrom references, make a bunch of those, and start at 15 degrees, get it to equilibrate, start to get these different references to diverge, and then funnel all the way down to 1 degree. And at some point, things would get constrained, but I don't care, because in the first round, it would be very coarse differences. And usually, I would sort out the junk from the real stuff that way, having identical references to start with, but starting at very low resolution and funneling down slowly as possible. Yeah?
Do you know why the search range is a set of fixed values? What's the reason for that?
It's because basically the program only searches those values and basically goes down by a factor of 2 each time. So you start 15 and 7.5 and then 3.75 and so on. So it's just basically trying to fill the grid by factor of 2 every time. So there's no specific reason for it. CryoSpark uses a different optimization where it looks for the optimal on the whole sphere and funnels down to the optimum basically in one shot by, I think, a Monte Carlo type algorithm, if I'm correct. And so CryoSpark does not really have that issue. Now, when you look at small differences, you might want to do local classifications, where you only look at plus minus 1 degree, at a 1 degree range, for example, to look at very small differences. Because, for example, you're masking one region, and therefore, if you were to look at the global range, you would misalign your particles. And so that's a case where RelyOn is very good at doing that, because you can say, I'm only looking at 1 degree, plus minus 5 or 10, I can mask and look at a very local region and do a very careful classification, all the way down to looking at one helix pitching a little bit in gamma secretase. What you can see that in Strauss-Cheres's paper on signal subtraction. So you can go very, very, very local. In CryoSpark, you cannot do that. Therefore, you cannot go do very local classifications, because it will always start at the global range. So you basically realign your particles. So if you mask them, they get completely misaligned, and that's too bad for you. I think they're trying to get a local classification. Now they already have local alignment. So the first step is there to get a local classification in CryoSpark, but it does not exist yet. Yeah, I think that, so that's one very important aspect. The second very important aspect, and I think I'll stop there, is at what resolution do you do your classification? It will, depending on what resolution you use, the kind of features you will classify will be very different. So in RelyOn, for example, if I started at 100 angstrom and funnel down without any restriction, I would basically funnel down to one super sharp ribosome and everything else being garbage. And if I keep doing that, I would always get all my data to one reference, and all the other one would be a much smaller subset of the data, because basically it would drive, like the high resolution would drive all the classification. So getting the core of the ribosome at high resolution would be all it's looking at. And so therefore it's very important to say, okay, is that what I want? And then fine. Or do I want to look at more global differences, much larger differences, and then you want to filter your reference to maybe 20 angstrom resolution or 15 angstrom resolution, where it cannot look at the high resolution and it will only look at the larger changes. Now it's getting tricky for small proteins, because to align a protein properly, and that's first described in Rosenthal and Henderson 2003, you need around 15 angstrom resolution. And so for a ribosome, you can go all the way to 20 angstrom. For a small particle, you might need 10 angstrom or even maybe 8 angstrom resolution to actually be able to align that particle properly. And so with small particles, you're constrained, because you cannot kind of do your classification at 20 angstrom. It will not align the particles at all. I think 12 angstrom might be the limit for quite small particles, like, I don't know, a GPCR or something like that. But you cannot go lower than that. And so that's a very important parameter in any classification, both in CryoSpark and in RelyOn. And what you're looking at in CryoSpark or RelyOn is the resolution you use to align the particles. So it's max align res parameter, or max expectation resolution in RelyOn. And you want to set that to a bunch of different resolutions and do different classifications at those different resolutions and see what the result is for each of them, because the result will be quite different. Okay, I think I will stop there, because that's, I would say, the most important part of the whole thing.